Hello everyone, my name is David and today I'll be presenting my honors project on nickel palladium and nickel gold as hydrogen evolution reaction catalysts. Okay, so to begin, climate change is one of the largest problems that humanity is facing at the moment. It's causing extreme weather, biodiversity loss, social inequality, and much more. The energy transition is something that is needed to mitigate climate change by reducing the amount of fossil fuels that we are using to produce energy, which are emitting large quantities of greenhouse gas as well as carbon dioxide. So we need to transition away from these energy sources towards more renewable and sustainable energy sources. Hydrogen is a key prospect for the energy transition. It's a clean energy source that can power vehicles, can store renewable energy. It's also used today in many industrial processes and chemical refineries. So 95% of today's hydrogen is produced through a process called steam reforming. That is a largely carbon dioxide emitting process. Most of this hydrogen is used in industry, which is a sector that is ripe for decarbonization. So we would like to generate our hydrogen in a clean way. And one way that this can be done is through electrolysis of water. So this is a typical electrochemical circuit that can apply a voltage that splits water and evolves or creates hydrogen, if you will, at the cathode and evolves oxygen at the anode. This process can be driven by a catalyst, which is the topic of our discussion today. So the current best catalyst for the hydrogen evolution reaction is platinum, which is extremely non-earth abundant and very expensive. So this is a barrier to scaling up the reaction. So we'd like to look towards other catalysts that are less expensive and can be employed at scale. So nickel is one of these catalysts that we would like to investigate as an alloy to assess its hydrogen evolution reaction activity, because it's low cost, basically owes it to a high scalability potential. So our hypothesis is that we expect each bimetallic catalyst that we have investigated to outperform nickel alone for the hydrogen evolution reaction. So our main objective is to analyze and compare nickel-rich catalysts for their hydrogen evolution reaction performance. So nickel palladium and nickel gold supported on carbon are the main catalysts that we have studied. It's important to note that these compositions are nickel rich, which keeps the cost low. And this work hasn't been done before, but has been supported by density theory calculations, which predict their performance in the hydrogen evolution reaction. So our first aim is to test different proportions of these bimetallics. We have not gone less than 80% atomic mass of nickel in either of these catalysts. Our second aim is to compare the efficiency, rate kinetics, and stability of each of these catalysts using voltammetry plots. So what is voltammetry and how did we perform these experiments? It starts with the glossy carbon working electrode, in which our catalyst is deposited onto the surface. And this working electrode is placed in a 3-electrode electrochemical cell, along with a counter electrode and a reference electrode. Through this electrochemical cell, we can apply voltage from a potentiostat. Here we can see the stepwise reaction of the hydrogen evolution reaction occurring on the surface of the working electrode. This is where reduction and oxidation is occurring and where hydrogen is effectively being produced. So by applying different amounts of voltage and setting different parameters, we can obtain different voltammetry plots. And so these plots help us analyze the catalyst activity, rate kinetics, and stability. So the first result that we've obtained is the characterization of our catalysts. So this is STEM imaging and EDS mapping that is essentially proving that we have nickel, gold, and that this composition of our catalyst is supported on carbon. So we can see that both of our catalysts do include nickel, the noble metal, in this case gold, in this case palladium, and they are both supported on carbon. So this is the first catalytic performance linear sweep voltammetry plot that we've obtained. So this type of plot essentially compares voltage to current density, which is synonymous to activity. So the voltage here on the x-axis, we can think of this linear sweep voltammetry plot as basically a comparison of activity. So the less voltage that it requires to produce the same amount of current density, the more active our catalyst is. So we can see platinum here requires the least amount of voltage to produce the same amount of current density. So if we're to draw a line through this 10 milliamperes per centimeter square line here, or activity level, we can see that platinum is the most active. Next is nickel 80, gold 20. So the highest percentage of gold being the most active after platinum itself. And then as we decrease the amount of gold in our catalyst, the activity decreases. But each of these catalysts here outperforming nickel alone for the hydrogen evolution reaction, according to these LSVs. And then with palladium, we can see the same trend. So nickel 80, palladium 20 in this case being the most active, and also more active than the nickel 80, gold 20 version over here, which is just close to negative 0.2 millivolts, while our nickel 80, palladium 20 is around half that. So, or almost at least half that. And so, yeah, we can see that a general trend of increasing the amount of noble metal in our catalyst increases the activity. And it's important to note that this is in 1 molar KOH solution. So these are Tafel plot, or is it a Tafel plot that depicts the rate kinetics of our catalysts. Essentially, the lower the slope is for these Tafel plots, the better the rate kinetics. All we've done to create these plots is taken the log of current density, or the activity, plotted here on the x-axis, and relating it to voltage. So the lower the slope, the better the rate kinetics. In this case, platinum, again, having the lowest slope and the best rate kinetics. And then we can observe a similar trend as we saw with the LSVs, where nickel 80, palladium 20 is outperforming the gold 20%. So lower slope here. We can also see a similar trend as we saw with the activity, where the least amount of voltage is required for platinum to produce the same amount of activity, followed by palladium, and then gold and nickel itself here at the top, with the worst rate kinetics and the most amount of voltage required to produce the same amount of log current density. Okay, and this is also in 1.0 molar KOH solution. Next, we have these cyclic amperometry plots that assess the stability of our catalysts over 24 hours. So here we can see we applied a constant potential of negative 0.3 volts over a period of 24 hours. And we can assess how the activity held up over these hours to essentially evaluate the stability of our catalyst. So we can see nickel 80, palladium 20 remaining extremely stable over this 24-hour period, while gold, the activity output changed slightly over this time period. So nickel 80, palladium 20 being more stable than gold, but both catalysts relatively stable in 1.0 molar KOH. This here is just a comparison between 1 molar KOH and 0.1 molar KOH activity. So it's a quantification essentially of the LSV type plots. And we can see that in 1 molar KOH, each catalyst requires less voltage than it would in the 0.1 molar KOH to produce the same amount of current density, which is 10 milliamperes per centimeter squared. So what this tells us is that our catalysts are more active and more efficient in 1 molar KOH solution, so a higher concentration of ions than in the 0.1 molar KOH solutions. And this is due to just that. There's a higher concentration of ions which are participating in the reaction and driving it forward. Cool. So coming to some conclusions here. Nickel palladium and nickel gold bimetallics have a lower onset potential than nickel alone. So that relates directly to the activity. Onset potential is another term for activity. So they are able to produce more hydrogen with less input, as we saw with the linear speed voltammetry plots. Next, both these catalysts are more kinetically efficient. So as we saw with the Tafel slopes, nickel palladium and nickel gold far exceed that the rate kinetics of nickel on its own. We also saw that both catalysts are stable for 24 hours. So nickel palladium being slightly more stable than nickel gold, but both are more stable. And these are all important for the overall picture, which is to drive down the cost of hydrogen production through using more efficient and active catalysts that can be scaled up and used for wide scale or widespread electrolysis in comparison to other polluting methods of like steam reforming for producing hydrogen. Perfect. So some of our future directions are to use density functional theory calculations and incorporate this into a paper that we're publishing. This is in collaboration with the Argentina Universidad Nacional del Sur, which is providing these density functional theory calculations on our catalysts. So these are basically theoretical calculations that have to do with the hydrogen absorption energy of our catalysts, and is essentially required to publish in high impact journals. And we would also like to test these catalysts in an electrolyzer, and this could better assess the catalyst potential for a larger scale hydrogen production. So we've done these reactions in 3 electrode electrochemical cells, which is essentially just a model reaction for the actual vessel in which these the hydrogen evolution reaction should take place, which is an electrolyzer, because this is all framed in the context of scale. We would like to scale up hydrogen so that we can employ it on a national level to decarbonize different sectors. So thank you, everybody. Thank you to Mohammed and Dr. Baranova, who have helped me with this project. And I will now open the floor to some questions.